During a slow routine drive across Gale Crater on Mars, the Curiosity rover rolled over a single rock, and the data that came back was so strange. The entire science plan had to be ripped up and rewritten. In this video, you're going to follow that moment step by step, from one crunch under a rover wheel to a discovery that forces us to rethink what Mars was and what it might still be hiding. How does a tiny crunch under a rover wheel turn into one of the biggest shocks in Mars science? You're riding along with Curiosity in Gale Crater, and nothing about this drive is supposed to be exciting. The rover is crawling at about 0.04 meters per second. That's roughly 0.09 miles per hour, slower than an average walking pace. The terrain is the usual Martian mix: dusty ground, scattered rocks around 10 centimeters high, about 4 inches, small enough that mission planners are happy to roll straight over them. This is standard housekeeping on Mars: drive a bit, take some images, maybe line up the next science target, repeat. For the team, this kind of sol is background work, the kind you almost take for granted after years on the surface. But that calm is exactly what makes the next few seconds so jarring, because a completely ordinary move is about to produce something that looks anything but ordinary. So what actually happens when that heavy, slow, nuclear-powered machine finally meets the wrong rock? Curiosity's aluminum wheel, about 50 centimeters across, 20 inches or so, climbs up onto a fist-sized rock roughly 10 centimeters wide. The rover's total mass is around 900 kilograms, close to a small car at about 2,000 pounds, but because Mars has lower gravity, the effective weight is about 340 kilograms force, around 750 pounds force. A good fraction of that presses down through the wheel onto that one unlucky rock. The contact area is small, so the pressure spikes, and in that slow motion press, the rock doesn't gently chip. It fails hard, it fractures suddenly, releasing stored stress, bursting into sharp fragments with flat, clean faces. It's like hitting tempered glass, but slower and colder. The wheel finishes the step, rolls off, and the rover's cameras, still following their routine image plan, catch the aftermath on the ground. But if rocks break all the time under rover wheels, why does this particular break immediately set off alarm bells? As soon as the images come down, you see the usual red-brown dust around the break, the typical rusty colour of iron oxides that coat almost everything on Mars. But in the centre of the impact zone, the freshly exposed pieces are wrong. Mixed into the broken rock are bright, sharply edged shards that look yellow, not red, not grey, not the dull tones you've seen for years. Their brightness, their reflectivity, is much higher than the surrounding soil. In simple terms, they bounce back maybe twice as much sunlight as the dusty ground around them. Even in a quick-look thumbnail, these pieces stand out so clearly that your eye goes straight to them. On a planet that has been visually predictable for decades, this is like seeing a flashing warning light in the middle of a dusty road. If Mars is supposed to be a red, dusty world, what does it mean when you suddenly see neon-like yellow cutting through that background? On Earth, colours like this are usually a clue. Bright yellow minerals often mean sulfates, evaporites, or some kind of chemically concentrated material, things that form when water evaporates and leaves behind the dissolved stuff it was carrying. In a lab or in a salt flat, that's expected. On Mars, in a random field of rocks inside Gale Crater, it's a serious hint that you've just exposed something that has gone through an extreme process. The geometry of the shards, the sharpness of the edges, and the very clean colour together tell you this is not just dust on a surface, this is something that was locked inside the rock and only revealed when the wheel crushed it. For a team trained to read tiny visual clues, this is the moment where routine ends and urgency begins. So once you see something that visually screams special, how fast can a rover actually react on a planet where everything is planned a day in advance? Curiosity doesn't spin around like a person, but its mast and arm can be repointed with a new command sequence. The first step is context, so MastCam, the main colour camera system, gets tasked to zoom in. It can resolve details down to fractions of a millimetre, around the thickness of a credit card, so those yellow crystals are now seen in close-up. You can see clean faces, crisp edges, and how they sit relative to the rest of the rock fragments. The field team on Earth updates the next Sol's plan. cancelling or delaying lower priority activities to lock more time onto this one spot. At the same time, ChemCam, the laser and telescope combo on the mast, is pointed toward individual crystals. Its laser can fire from up to 7 meters away, about 23 feet, so the rover doesn't need to move much. The idea is simple: hit the bright pieces directly, turn a tiny bit of them into plasma, and let the spectrometer read the light. But even with all this hardware, how do you know this isn't just some slightly unusual rock that will turn out to be boring once you see the numbers? The first laser shots hit, each one vaporizing an area less than 0.5 millimeter across, about the width of a pencil lead. The plasma glows for a fraction of a second, and the instrument splits that glow into a spectrum, which is basically a barcode for elements. Curiosity has done this hundreds of times before on bee salts, mudstones, veins, dust, you name it, and the team has built up a library of what normal Martian targets look like. When the data from these yellow shards arrives, the pattern is off. The peaks at wavelengths associated with sulfur are strong, maybe chlorine too, and the ratios between elements do not fit the usual profiles. You're not just seeing a little more sulfur than average, you're seeing a signature that sits far away from the tight clusters of past measurements. If the planet has given you thousands of normal spectra, what does it mean when this one refuses to fit into any of those groups? Within less than one Martian sol, about 24 hours and 40 minutes, the internal description of this feature shifts. It's no longer a random rock the wheel broke. It becomes a chemically extreme object, and maybe the most extreme Curiosity has ever touched. The bright colour, the high reflectivity, the odd geometry, and now the strange elemental fingerprint all stacked together. This is not a small variation on normal Martian rock, this is a serious outlier. People start asking new questions. Is this a concentrated sulfate deposit from a shrinking lake? Is it an unusual chloride or perchlorate-rich phase? Did we just expose a mineral that records a very specific, very harsh kind of water that had been trapped and hidden for millions or even billions of years? And that leads to a bigger, more uncomfortable thought. If one slow wheel crunch can reveal something this extreme by accident, what does that say about what Curiosity, this 900 kilogram rolling lab, can actually do when it deliberately turns its full set of instruments on a target like this? How does a slow, car-sized robot that can barely crawl faster than you walk end up becoming one of the best field geologists in history? Curiosity is basically a 900 kilogram rolling lab, about 899 kilograms if you want the exact number, roughly the same mass as a small car around 2,000 pounds. On Earth, that much mass presses down with 1 g of gravity. On Mars, gravity is only about a third of that, so the rover weighs roughly 340 kilograms force, about 750 pounds force on the ground. That change matters, because every wheel step, every rock it climbs, and every fracture it causes is tuned by that lower pull. The body stretches about 3 meters long, close to 10 feet, with a mast sticking up to around 2.2 meters, about 7.2 feet, so if you stood next to it, the head of the rover is basically eye level. And here's the key point: this thing is not just a remote-controlled camera on wheels. The whole frame is packed with instruments, sample handling systems, and computers that can take a rock, strip it down into data, and then turn that data into a story about water, climate, and time. When that wheel crushed the strange yellow rock, it didn't just drive past an odd colour, it brought that object into reach of an entire laboratory. But how do you keep a lab that heavy, in a place that hostile, running for years with no solar panels and no refuel? Curiosity runs on a nuclear heart, a radioisotope thermoelectric generator on its back. Inside, a chunk of plutonium-238 slowly decays, releasing heat. Thermocouples turn that heat into electricity, around 110 watts of power, about the same as a bright household light bulb. On paper, that sounds weak for a car-sized machine. On Mars, it's enough. There's no air conditioning, no power steering, no traffic lights. The rover moves slowly, its motors are efficient, and it doesn't waste energy on things humans need. That constant 110 watts runs the computers, the heaters that keep sensitive parts above freezing, the wheels, and the science instruments, all managed with careful scheduling. At the same time, the generator's waste heat keeps the internal systems from freezing solid in nights that can drop below -70 degrees Celsius, around -94 Fahrenheit. That tiny constant power stream plus patience lets Curiosity crawl kilometers over Martian years, building up a timeline of the planet layer by layer, sample by sample, crunch by crunch. So when that weird yellow crystal shows up under a wheel, what kind of tools are actually ready to attack it? You've got a full arsenal aimed at that one broken rock. Marscam gives you colour images and context. It tells you exactly where those yellow shards sit, how big they are, what angles they break at, and how they relate to nearby layers. ChemCam fires its laser at specific spots, vaporizing areas less than 0.5 millimeter across, then reads the light from the plasma to find out which elements are there. A PXS, the alpha particle X-ray spectrometer on the rover's arm, can be placed just millimeters from the surface, bathing the target in alpha particles and X-rays to get another elemental breakdown, averaged over a slightly larger patch. Chi-Min, the chemistry and mineralogy instrument inside the rover's body, can take powdered rock and use X-ray diffraction to figure out how the atoms are arranged, which minerals are present, which crystal structures you're dealing with. And Sam, the sample analysis at Mars Suite, can heat samples, sniff the gases that come off, and look for organics and other volatile compounds. That single mysterious object has just landed in the middle of a sensor lineup that can, if you feed it the sample, go from colour to elements to crystal structure to gas release, covering everything from big picture context down to the arrangement of atoms in the lattice. Here's the part that really bothers scientists in a good way. How does one of the most important samples show up not from a perfect plan, but from pure chaos? Normally, targets are chosen carefully. Teams study high-resolution images, pick out layered outcrops, veins that cut across rock, fine-grained mudstones that might preserve old lake sediments. They design contact science campaigns, put the arm down gently and sometimes risk drilling. Everything is controlled. This time it's the opposite. The rover simply drives, a wheel hits a rock, the rock fails, and you get a cross-section through its interior with zero planning. Scientifically, that's gold. Surfaces on Mars are often altered. Ultraviolet light, cosmic rays, and dust abrasion can change the outer few micrometers or millimeters of a rock over millions of years. They can darken it, coat it, and erase subtle features. When the wheel breaks that rock open, you get fresh crystal interiors, sharp and clean, that may not have seen direct radiation since they formed. You're looking at material that has been sealed away, shielded by the rock itself. That random fracture gives you something no careful brush of the surface can match, a direct window into the original chemistry before the planet's harsh environment started to grind it down. If randomness can expose something this valuable, what does that say about how much we've been underestimating the planet? Curiosity isn't on Mars to chase pretty colours or collect cool rocks for social media posts. The mission has a strict core question. Did Gale Crater once host environments that could have been habitable? Places where life as we understand it could have survived? The crater is already known to have held a lake tens of kilometres wide, on the order of dozens of miles, in its past. The rover has seen mudstones, fine laminations, and minerals that point to long-lasting water. How in that same setting, you suddenly find a crystal that looks like a chemical extreme, something that might only form when water gets highly concentrated, when a lake shrinks, when salinity and acidity spike, or when brines move through rock in specific harsh ways. That shifts the stakes fast. You're no longer just mapping where the lake was, you're asking how that lake evolved, how it evaporated, how its chemistry changed over the time, and whether it passed through the phases that were far more aggressive, far more energetic than your models assumed. A rock like this might mark a point where the environment crossed from friendly to brutal, from mild water to extreme brine, and that boundary is exactly where questions about habitability and prebiotic chemistry get sharp. And once you see that this accidental sample might rewrite the history of an entire Martian lake, the next question hits hard. What does that bright yellow really mean on a planet that's supposed to be red? How much trouble can one wrong colour cause on a whole planet? On Mars, colour is usually boring in a very consistent way. Most of the surface is covered in iron oxides, minerals like hematite and related phases, that give you that stable red-orange dust. The rocks underneath are often basaltic, dark grey to nearly black, the same kind of volcanic rock you find in Hawaii or Iceland. When water has been involved and you get hydrated minerals, the tones shift a bit. They can go paler, more tan or light grey. But even then they stay in the same family, muted, dusty, nothing close to a bright lemon yellow that hits your eye right away. So when you see shards that really are that yellow, and they stay yellow even when you zoom in, you're not just seeing a small colour variation, you're seeing chemistry pushed into an extreme corner. On a red planet, that kind of yellow usually only appears when something very special has happened to the rock. So the question becomes, what kind of process on any planet produces colours that strong and that pure without any help from biology? On Earth, bright yellow minerals very often mean sulfates or related compounds. Jarosite is a classic example, an iron sulfate that can form in acidic water, such as in acid mine drainage zones, volcanic environments, or certain drying lakes. You also get yellowish iron sulfur minerals where water, rock, and oxidizing conditions meet. The common theme is not the name of the mineral, it's the environment it needs. You need liquid water, you need dissolved ions like sulfate, iron, maybe chlorine, and you need strong chemical gradients, differences in pH or oxidation state, to go from muddy mixed sediments to bright, crystalline, chemically clean yellow phases. Nature has to concentrate things. It has to run a process like evaporation in a lake, hydrothermal circulation through fractures, or slow drying of brines in confined pockets. The more concentrated the water becomes, the more it starts to drop out specific minerals as clean, well-formed crystals. That is what these shards are hinting at. Not just water was here, but water here got pushed into a very concentrated, possibly harsh state. Now you have to ask, can you actually see that intensity in the data? Or is your eye just being tricked by a funny lighting angle? The rover's cameras do more than take pretty pictures. Marscam has filters that let it measure brightness at different wavelengths, so you can build simple reflectance curves, not as detailed as a full lab spectrum, but enough to see if something is truly brighter and differently coloured, or just a dusty surface with a glare. The yellow crystals show higher reflectance. They bounce back more of the sunlight that hits them compared to the surrounding regolith. When you look at them through different filter combinations, the contrast stays. They don't wash out. ChemCam's remote micro-imager can then zoom in and show texture and micro-contrast, confirming that what you're seeing is intrinsic to the material, not a thin coating. When you compare their reflectance spectrum to the baseline Martian soil, the curve is sharper, with more defined changes, instead of the broad, smooth, dusty smear that regular soil produces. In simple terms, the sensors are telling you the same thing your eyes are telling you: this material interacts with light in a different way than the background, and that difference is tied to composition and structure, not a camera glitch. But even if the chemistry looks extreme, how are these crystals still so clean and sharp on a planet that is constantly trying to destroy delicate things? Mars is not gentle. Near the equator, daytime temperatures can climb to around 0 degrees Celsius, 32 degrees Fahrenheit, then drop at night to around minus 70 Celsius, about minus 94 Fahrenheit. That swing happens under an atmosphere with a pressure of around 600 pascals, less than 1% of Earth's sea level pressure. At those pressures and temperatures, many volatile minerals are unstable. They dehydrate, they break down, or they get mechanically destroyed by thermal stress. On top of that, dust storms move fine grains at tens of meters per second, tens of miles per hour, sandblasting exposed surfaces over millions of years. Ultraviolet light and cosmic rays damage crystal structures and surface chemistry. So if you're seeing crystals that are intact with sharp edges and clean faces, not rounded, not crumbling, that immediately tells you something. Either they are relatively young in terms of exposure age, maybe recently uncovered by erosion, or they are made of a phase that is unusually stable under Martian conditions, or they were shielded inside the rock until Curiosity's wheel broke them open. None of those options are normal background noise. All of them imply a specific history that preserved them against a pretty hostile environment. So now the colour is not just a visual oddity, it's a direct clue that points to time, stability and protection. And that pushes the next question: what exactly are you looking at? And what does each option say about Gale Crater's water? If the crystals turn out to be sulfates, they can act like a chemical recorder for ancient water. Their structure and composition can encode pH, how acidic or alkaline the water was. They can capture salinity, how many dissolved salts were in each litre, and they can reflect oxidation state, how electron-rich or electron-poor key elements like iron and sulfur were. On Earth, reading those details tells you if a lake was mild and life-friendly, or corrosive and extreme. If instead the crystals are something like unusual chloride or perchlorate hydrates, that points toward very salty brines, freezing and thawing cycles, and perhaps water that stayed liquid only because it was loaded with dissolved salts. Perchlorates, for example, lower the freezing point of water and are known to exist on Mars. Each mineral type locks in a different version of the lake's history, a different stage of evaporation, a different style of brine evolution. Either way, the bright yellow here is not decoration. It is a warning label that says, in this exact spot, Mars once ran a serious chemical experiment, over distances measured in kilometers and depths measured in meters, not over a few centimeters of rock. The planet didn't just have water, it pushed that water through phases that could completely change how you think about habitability and chemical complexity in Gale Crater. And if a single colour patch can carry that much information about extreme chemistry, you have to ask, what happens when you combine that signal with lasers, X-rays, and a full mineral fingerprint from the same rock? How do you actually prove that a weird-looking rock is genuinely alien in its chemistry, and not just your eyes playing tricks on you? The first real punch comes from ChemCam. Its laser is built for exactly this kind of moment. It locks onto one of those bright yellow crystals and fires pulses with enough energy to vaporize a tiny spot on the surface less than 0.5 millimeters across, roughly the thickness of a pencil lead. Each pulse turns that microscopic area into a glowing plasma, a tiny cloud of ionized gas hanging over the crystal for a brief instant. The spectrometer then looks at that glow, splitting it into its component colors. In that spectrum, specific wavelengths light up based on which elements are present: sodium, magnesium, aluminum, silicon, sulfur, calcium, potassium, and others. By measuring the intensity of those peaks, ChemCam gives you the elemental composition of that exact point, with spatial resolution at the scale of millimeters and even below. You're not getting an average over a big chunk of rock. You're reading individual crystals, one tiny laser spot at a time. So what happens when you compare this fingerprint to everything you've ever seen on Mars before? Curiosity has used ChemCam on hundreds of targets, maybe thousands by now. Basalts, mudstones, cross-cutting veins, dust coatings, and loose soil. For all of that, scientists have built a library of normal spectra, clusters of data that tell you what typical Martian rocks look like in terms of element ratios. When you hit regular basalt, the pattern is predictable. When you hit vein material rich in calcium sulfate, again you know the basic shape. But when the laser hits these yellow shards, the returned spectrum doesn't want to sit in any of those familiar groups. You might see sulfur lines much stronger than usual, a sulfur to calcium ratio that is way off the standard gypsum-like behaviour, or chlorine features that are too high to be explained by simple dust contamination. You can plot this composition on diagrams the team uses every day, and instead of landing in a dense cloud of pass points, it sits way off in a corner by itself. That's the spectral version of scanning a barcode at a store and having the register say, "Item not found." Now you have to ask, is this just one weird little pocket, or is the whole piece of rock chemically extreme? That's where EPIXS comes in, the alpha particle X-ray spectrometer on the rover's arm. Curiosity moves closer, carefully positions the instrument head just a few millimeters from the exposed crystals, and starts a new measurement. A PXS works differently from ChemCam. It bathes the target in alpha particles and X-rays, then detects the secondary X-rays emitted by the elements in the rock. From that, it builds another elemental breakdown, but this time averaged over a slightly larger patch, not just a single pinpoint. This is critical, because ChemCam is like poking individual pixels, while a PXS is like looking at a small cluster of pixels together. If ChemCam saw ultra-pure sulfur-rich spikes in a few spots, a PXS tells you whether that is just tiny veins or coatings, or whether a bigger chunk of the rock is also pushed into that extreme composition. When both instruments independently say, "This material is way off the normal curve," your confidence grows that you're not just looking at a thin film or a measurement glitch. But elemental composition is only half the story, right? Because the same elements can be arranged into completely different minerals. If Mission Control decides it's worth the risk, the next step is drilling, and that's where Che-Min, the chemistry and mineralogy instrument, has a chance to turn this from weird chemistry into possibly new mineral. Drilling is not a casual move. It uses power, it stresses the hardware, and it has to be justified. If the team goes for it, the drill collects powdered material from the rock, including those yellow crystals, and moves the sample inside the rover into Che-Min's tiny analysis cell. Che-Min shines X-rays through the powder and measures the angles and intensities at which those X-rays are diffracted. That diffraction pattern is like a structural fingerprint. It tells you how the atoms are arranged in three-dimensional space, which crystal structures are present, what minerals you actually have. On Earth, labs use this method every day to distinguish between minerals that have the same basic elements but different structures. If Che-Min's pattern matches known Martian sulfates, like those seen elsewhere in Gale, you can slot this into the existing catalogue. But if the diffraction peaks don't fit standard Martian sulfates or even common terrestrial minerals, then you're not just talking about a new mineral on Mars. You might be looking at a crystal structure that has never been documented in any sample from Earth at all, a phase that only forms under Martian-style conditions of pressure, temperature, and chemistry. At this point, the stakes are obvious, but there's still a brutal question you have to answer honestly. How do you know all of this isn't just your instruments acting up? To claim you've found the most mysterious object, a genuine chemical outlier, you cannot bet everything on a single strange data set. You have to test the anomaly from every angle and try to kill it. That means firing ChemCam at multiple crystals on different parts of the broken rock, checking if the odd composition repeats or if it was a one-off. It means repositioning a PXS, doing more than one integration, maybe on slightly different spots, and checking if the numbers are consistent. It means using Mastcam to confirm that you're really hitting the yellow material and not some mixed area. It also means comparing all of this to calibration targets on the rover itself, pieces of known composition that were bolted onto Curiosity before launch. If the instruments read the calibration targets correctly, and keep doing so over many sols, then the problem is not the hardware. The team also looks at environmental factors, dust on optics, temperature effects, anything that might bend the numbers. If, after all of that, the yellow crystals still show the same extreme sulfur, the same odd chlorine, the same out-of-family pattern in both ChemCam and APXS, and if Che-Min, if used, returns a diffraction pattern that refuses to match standard libraries, then you've crossed a line. You've moved from "this might be noise" to "Mars is really doing something here that we did not predict." And once you accept that the instruments are telling the truth, and that truth is a crystal that doesn't fit your catalogue, the next problem is bigger. Where on Mars could something this extreme have actually formed? And what kind of ancient environment was powerful enough to grow it? How big does a scar on a planet have to be before it becomes a history book instead of just a hole? Gale Crater is not a small dent. It is about 154 kilometers across, roughly the distance from New York City to Philadelphia, or London to Birmingham. That whole area is one gigantic sediment trap, a basin where anything carried by water, wind or gravity can end up and stay. In the middle sits Mount Sharp, a central mound that rises about 5 kilometers high, around 3.1 miles. That mound is not a single block of rock, object is a stack of layers, one on top of another, piled up over hundreds of millions of years. Each layer was once a surface, once a place where dust settled, water flowed, or a lake stood still. When you look at Mount Sharp from Curiosity's cameras, you are not just seeing a mountain, you are seeing a vertical timeline, a three-dimensional climate record, carved into stone. The yellow crystal that got crushed under Curiosity's wheel is one tiny piece of that record, and its real meaning only makes sense if you know where in that massive stack it was born. So how sure are we that this crater actually held a lake, and not just dust blowing around for ages? Curiosity has already answered that. The rover has driven across and drilled into rocks that look, under close inspection, exactly like lake sediments on Earth. Mudstones with very fine grains tell you that particles settled out of quiet water in depths from a few centimeters to meters. Cross-bedded sandstones show how currents moved and shifted over time. Fine laminations, paper-thin layers show gentle, repeated deposition, like slow settling in a calm body of water. When you look at the grain sizes and the mineral mixes, you see a pattern that fits a long-lived lake, not a brief flood. The data suggests this lake persisted for at least thousands to millions of years. That means a body of water tens of kilometers wide, perhaps around 100 meters deep, roughly 328 feet, existing long enough for complex chemistry to run again and again. This is not a puddle that dried up in a season. It is a stable environment, a chemical factory that had time to change its own conditions. Now, the key question is, within that huge timeline, when did the rock that holds the yellow crystals actually form? The crushed fragment under the wheel is not floating in isolation. It sits in a specific context, near certain layers and far from others. If it is close to clay-rich strata, that points to a time when the lake water was neutral to mildly alkaline, relatively friendly, something closer to Earth-like conditions. If it is near sulfate-bearing layers, that points to a much later stage, when water was evaporating, concentration was rising, and the chemistry was shifting toward more acidic, more aggressive brines. If that bright yellow material lies within or just above a sulfate horizon, that is a loud signal. It says late-stage evaporation product. In other words, this rock crystallized when the lake was not calm and mild anymore, but when it was shrinking, concentrating salts, and crossing thresholds where new minerals drop out of solution. The exact vertical position in the stack turns a weird crystal into a timestamp. So what was the lake actually doing to the water to create something this extreme? Was it just sitting there? Or was it actively changing every litre over time? As the lake in Gale Crater evaporated, the dissolved ions in the water did not disappear, they got left behind in the shrinking volume. Calcium ions, magnesium ions, sodium ions, sulfate ions, chloride ions, and probably perchlorate ions all started at some initial concentration. As the water volume dropped, those concentrations could climb by factors of 10, 100 or more. At certain thresholds, specific minerals start to crystallize like steps in a sequence. On Earth, you see this clearly in salt flats and enclosed basin lakes that are drying out. First carbonates, then sulfates, then chlorides, and so on. The exact order depends on pH, temperature, and the original mix. On Mars, in Gale's Lake, the same physics and chemistry apply. That means the ancient water was not just a passive background. It was actively reacting with rock, taking in ions, concentrating them, and then dropping them back out as new minerals. The sediments were not just a pile of mud, they were a chemical reactor running for very long timescales. And here is the part that really raises the stakes. Why does it matter that this chemical outlier showed up here in Gale and not in some random volcanic field? If you found bizarre yellow crystals in a region that looked purely volcanic, with no good evidence for past liquid water, you would still be interested, but the story would be narrower, maybe odd magmatic processes, maybe gas-rich vents, but finding them in Gale Crater, a site already established as an ancient habitable environment, is different. It means Mars did not just have a calm lake and then turn off the water. It means the same basin went through multiple phases, fresh to briny, more neutral to more acidic or alkaline, as climate changed and water came and went. Each phase carves out different chemical niches. Some are mild, where life as we know it could have an easier time. Some are extreme, where only very tough life or no life at all could hold on, but where chemistry itself becomes very rich. The yellow crystal suggests that Gale hosted not just a yes or no answer for water, but a whole series of changing conditions, some of which might push right up to the edge of what we call prebiotic, the kind of environment that can build complex molecules even if life never actually got started. And if one crater on one planet can cycle its water through that many chemical states, just to grow a single strange crystal we happen to crush, you have to ask, what was that water really like on a microscopic level, inside the brines that fed those minerals? How does fairly normal, almost drinkable water turn into something that can carve a planet's surface and grow extreme minerals? Early in Gale's history, the lake water probably looked a lot closer to what you'd call normal. Total dissolved solids, the amount of stuff dissolved in each litre, might have been just a few grams per litre, in the same ballpark as many lakes on Earth. As climate shifted, as Mars lost atmosphere and cooled, that lake did not just quietly sit there. It shrank, shorelines pulled inward, depths dropped, inflow changed. Every time the water volume went down, the dissolved material stayed behind. Over time, those concentrations could climb from a few grams per litre to tens of grams per litre, and then to hundreds of grams per litre, reaching levels you see in the Dead Sea or the most hypersaline ponds in Antarctica. At that stage, each litre of water is not mild anymore. It is a chemical solution that aggressively reacts with rock, strips ions out of minerals, and exchanges gases with the atmosphere far more intensely. The lake at Gale, in its late phases, would not have been a place you think of as calm and harmless. It would have been a dense chemical soup, pushing against the limits of what water can carry before it starts dropping out strange crystals. But it's not just about how salty the water became, right? The important part is what kind of chemistry that water was actually running while it concentrated. pH and redox are the two big control knobs here. pH tells you how acidic or alkaline the water is. Acidic water with a low pH is very good at dissolving basalt, pulling out metals like iron, magnesium and calcium, and moving them around. More neutral or alkaline water behaves very differently. It tends to precipitate things out, forming carbonates and certain clays. Redox, short for reduction oxidation conditions, tells you how electron-rich or electron-poor the environment is. That decides whether sulfur in the water sits as sulfate, which is oxidized, or as sulfide, which is reduced. It decides whether iron is in a more soluble, reduced form, or in an oxidized form that wants to precipitate as minerals. On Earth, changes in pH and redox in lakes create banded deposits, different coloured layers that mark when the water chemistry flipped between states. On Mars, even subtle shifts in rainfall, evaporation rate, or volcanic gas release, for example injections of sulfur dioxide into the atmosphere, could have nudged Gale's lake from relatively benign conditions into phases that were far more corrosive or oxidizing. Each shift changes which minerals are stable and which new ones start to grow. Now add one more complication. What happens when all of this chemical action is taking place in a lake that spends most of its life below freezing temperatures? Gale is not some warm blue Earth-like lake. Average temperatures hover well below 0 degrees Celsius, 32 degrees Fahrenheit. The only reason you get liquid water at all for any length of time is because it is salty. Brines, water loaded with dissolved salts, can stay liquid down to around minus 20 degrees Celsius, minus 4 Fahrenheit, or even lower depending on the mix. When that briny water starts to freeze, the ice that forms is almost pure H2O. The salts get pushed out of the forming ice crystals and shoved back into the remaining liquid. That rejected material makes the leftover brine even more concentrated. Each freeze-thaw cycle repeats this process, creating pulses where the water becomes more and more loaded with ions, then partially melts, moves a bit, and refreezes again. On Mars, you have daily temperature swings, and you also have seasonal swings, so these cycles could repeat many times. The result is a natural enrichment machine, a distillation process that keeps driving ion concentrations upward, creating exactly the kind of supersaturated extreme fluids you need to grow unusual crystal phases like the ones Curiosity crushed. But even if the lake can do that, do you really get enough time to run all these cycles and build big, well-formed crystals instead of just thin coatings? Yes, because the timescales we are talking about are huge. Sedimentation rates in Gale may be slower than in many lakes on Earth, but they do not need to be fast. Even if you only stack a few tenths of a millimetre of sediment per year, over 1 million years that becomes hundreds of metres of deposits. Over tens of millions of years, you can build the kind of massive layered pile you see in Mount Sharp. Inside that thick stack, you do not have one uniform environment. You have localized pockets, small fractures where water moves differently, microbasins where liquid collects then evaporates, little depressions where brines can sit, stagnate and concentrate. In those pockets, if the water is super saturated, crystals can grow to sizes of centimeters, an inch or more, given enough time. The rock that ended up under Curiosity's wheel may have been one of those local environments, a tiny chamber where brine sat long enough to grow these bright, chemically extreme crystals, and then got buried and locked in as more sediment piled on top. When erosion finally brought it back near the surface and the rover rolled over it, you got a cross-section through a microenvironment that had been frozen in place for a very long time. So then the big question is, what does the single crystal actually remember about all of this? Is it just a pretty shape, or does it carry a record of the water that grew it? A well-formed crystal is not just a solid chunk of stuff. It is a structured record. Different ions can substitute into the crystal lattice, swapping in for each other depending on size and charge. The relative amounts of those substitutions can depend on temperature and salinity at the time of growth. Trace elements, present at very low levels, can sneak into certain sites in the structure, and their abundances can tell you about the composition of the fluid. Isotopes, different versions of the same element with slightly different masses, are even more sensitive. Ratios of light and heavy isotopes of oxygen, hydrogen, sulfur or chlorine can encode how much evaporation the water experienced, whether the fluid was influenced more by groundwater, surface runoff or atmospheric interaction, and whether the system saw multiple episodes of flooding and drying. If you could bring that yellow crystal back to Earth, into a full lab, you could attack it with high-precision mass spectrometers, electron microprobes, nanoscale imaging tools. You could read out, layer by layer, changes in temperature within a few degrees, shifts in salinity, and even count how many times the environment switched from wet to dry. It would be a chemical diary written not in ink, but in atomic substitutions and isotope ratios. Curiosity cannot do that level of detail on Mars. Its instruments are powerful but still limited compared to Earth labs, yet even with that limitation, the rover can still see enough to know that this is not an ordinary piece of evaporite. It is a condensed record of extreme water chemistry. And if this crystal has quietly stored that story for millions or billions of years, on a surface blasted by radiation and dust, you have to ask, how did it survive long enough for a rover wheel to expose it? And what does that say about the strange combination of protection and chance that made this discovery possible? How long can something delicate really last on a planet that is basically a giant radiation experiment? Mars does not have a global magnetic field like Earth, and its atmosphere is thin, less than 1% of our surface pressure. That combination means the Martian surface is exposed to cosmic rays coming from deep space and high-energy particles from the Sun. Curiosity carries an instrument called RAD, the Radiation Assessment Detector, and it has measured surface dose rates on the order of 0.2 to 0.7 millisieverts per day. For comparison, average natural background on Earth is a few millisieverts per year. So Mars is hitting rocks, dust, and any exposed crystal with doses that are hundreds of times higher than what you get at sea level on Earth. Over millions of years, that kind of bombardment breaks chemical bonds, knocks atoms out of place in crystal lattices, and slowly turns sharp structures into more disordered, damaged versions of themselves. At the surface, you expect mineral grains to become partly amorphous, meaning the original crystal structure gets blurred. So when you see yellow crystals that look clean and sharp, your first reaction should be, they have no business looking that good after this long under this much radiation. If the radiation is that intense, why don't we just blame it for everything and move on, instead of treating these fresh crystals as a serious anomaly? Because radiation damage has clear patterns. It affects the outer layers first, it builds up gradually, and if the crystals have been sitting at the surface for millions of years, you would expect to see dulling, micro cracks, and maybe even colour changes. Cosmic rays are deeply penetrating, but they still lose intensity as they go through material, so even a metre or so of rock or soil above a crystal will cut the dose significantly. That means if a crystal looks like it escaped damage, the simplest explanation is that it did escape, not by luck, but by being physically shielded for most of its life. The fresh, sharp look of those yellow shards suggests they spent the majority of their history inside the rock, not at the surface. That immediately pushes you toward a story where burial and later exposure matter a lot. And radiation is only part of the attack, so what happens when you add ultraviolet light on top of that? On Mars, ultraviolet radiation from the sun hits the ground with much less filtering than on Earth. The thin atmosphere does not block many of the shorter wavelengths that are more energetic and more damaging. UV photons don't go deep, but they are brutal to whatever is exposed. They break complex molecules apart, which is one reason organics on the surface are so hard to preserve. They can also change the colour and structure of some minerals, a process called photo-bleaching or photo-alteration. Given enough time, UV will fade bright colours, roughen surfaces, and help weaken crystal edges. Even at the low pressure of around 600 pascals, this effect still runs, slowly but relentlessly. Any mineral phase that is structurally weak or sensitive to light should, over geologic timescales, lose its crisp geometry and intense colour. Yet in the moment right after Curiosity's wheel crushes that rock, the exposed crystals look like they just grew yesterday, not like they have been sitting on an open plain for hundreds of millions of years. So if radiation and UV haven't had time to wreck these crystals, what about the mechanical side, the constant physical beating from the Martian environment? Mars is constantly sandblasting itself. Dust storms don't just turn the sky orange, they move particles at speeds of tens of meters per second, tens of miles per hour. Even in calmer conditions, small grains get lifted and dropped, scraping across exposed surfaces like a never-ending sandpaper. Over millions of years, this abrasion rounds off sharp corners, smooths out jagged edges, and grinds down delicate structures. Rock faces get polished, individual grains get chipped. On top of that, thermal cycling, daily swings from near 0 degrees Celsius, 32 degrees Fahrenheit, down to around -70 Celsius, -94 Fahrenheit, cause expansion and contraction. That flexing creates microfractures and spalls off little chips. Put this together, and any crystal that is fragile, or that sticks out from the rock, should not stay crisp for long on an exposed surface. It should end up covered by a thin layer of dust, partly broken, less reflective, and visually blended into the background. The fact that these yellow crystals appear sharp and angular immediately after exposure tells you that the sandblasting began only after the wheel did its job, not for millions of years beforehand. So how do you reconcile fresh-looking crystals with a surface that is anything but gentle? What kind of protection would they need? The cleanest explanation is shielding. Picture the crystal-bearing rock sitting buried under a layer of regolith, perhaps a metre or more thick, 3 feet or more for a very long time. That overburden would absorb a large fraction of the incoming radiation, deflect most of the sandblasting, and block direct UV entirely. Inside that shield, the crystals could sit in near original condition, their lattice intact, their colour preserved, their edges still sharp. Over geological time, slow processes like wind erosion or small impacts could strip away some of that cover, bringing the host rock gradually closer to the surface. Maybe fractures opened from thermal stresses or local tectonic adjustments, maybe small craters excavated nearby material. Eventually, the rock ends up shallow enough that a rover wheel pressing down with a few hundred kilograms of force under Martian gravity can break it open. When that happens, for the first time since the crystals formed, their interior faces are exposed directly to the sky. So when you look at the shards in Curiosity's images, you're not seeing a surface-altered mineral that's been cooked and battered for ages. You're seeing something much closer to the original formation state, like opening a sealed container after millions of years. But that leads to a more unsettling point. If this mineral phase is fragile or only stable in a narrow range of conditions, what does it really mean that it survived at all? If the crystal structure is robust, stable across a wide range of temperatures and pressures, preservation is still interesting but easier to accept. If, however, the analysis suggests this phase is metastable, meaning it prefers to transform into something else over time, or it is sensitive to heat, light, or slight changes in composition, then its survival becomes a serious puzzle. It is like finding an ice sculpture preserved in a desert cave, in a place that should have melted or shattered it long ago. The fact that it exists, intact, on Mars, hints that the combination of burial depth, local temperature, history, and chemical surroundings were just right for a very long time. Maybe the rock stayed at relatively constant temperatures, buffered by surrounding sediments. Maybe the pore spaces were filled with certain gases or minerals that helped lock the structure in place. Whatever the exact mechanism, it means the conditions that formed and preserved this crystal were not generic, they were special. And that is the real punchline here. The universe is not supposed to hand you pristine, well-preserved evidence from billions of years ago on the surface of a world this harsh, in a form that just happens to break open under a rover wheel moving slower than you walk. But that is exactly what seems to have happened. The crystal should have been erased, dulled, or destroyed long before Curiosity arrived, yet it wasn't. It waited, sealed up, till a nuclear-powered robot rolled over it and exposed a near-original sample of extreme Martian water chemistry. So if Mars is willing to protect something this delicate for this long, and then drop it in front of a rover by pure chance, you have to ask the next hard question. In a place like this, with water that extreme and energy gradients that strong, how close could the chemistry have come to something we would actually call alive? How far can you really push a rock before you have to start asking the life question, even if the mission wasn't built to answer it? Curiosity's job is habitability, not life detection. The core question is simple but strict. Could Mars have supported life at some point in the past, yes or no? It was never sold as this rover will find fossils or this rover will see microbes. These yellow crystals land exactly on that line. On Earth, some minerals form only through geology, no biology needed. Others are strongly influenced by microbes, either in how they start forming or in how they get altered later. Your job here is not to scream life or to ignore the possibility. Your job is to ask a harder, quieter question. Are these crystals just a strange outcome of brines and evaporation, or do they sit in a chemical niche where microbial life, if it ever existed on Mars, would have found a good home? So what would good home even mean for a microbe in a place this harsh? On Earth, microbes do very well anywhere there's a strong redox gradient, a difference in chemical potential between two states of matter they can tap for energy. They do not need sunlight, they just need a chemical staircase to walk down. Sulfur-rich brines where sulfate and sulfide coexist, iron-rich settings where iron flips between reduced and oxidized forms, chloride-heavy brines with changing oxidation states. All of these are power sources. Microbes can breathe sulfate, using it the way we use oxygen, or use iron as an electron shuttle. If the Martian crystals capture strong contrasts in sulfur oxidation state or iron valence, that is a big deal. It would mean the water that grew them was not chemically flat. It had built-in energy gradients, the exact thing biology loves to exploit. You can't see microbes in the crystal, but if the chemistry says there was a lot of usable energy here, that's the closest thing to a neon sign you're going to get on a dead planet. But chemistry is only one angle, right? What about the actual shapes and tiny structures inside the mineral? At very small scales, minerals that grow in the presence of life can look different from those that grow entirely without it. On Earth, You see micro-layering, tiny tubes, clumps that follow cell-size patterns, or textures that look like communities coated in minerals. Curiosity doesn't have an electron microscope, but it does have Machli, the hand lens imager on the arm. Machli can resolve features down to tens of micrometers, smaller than the thickness of human hair. That's enough to see whether the crystals are clean and uniform, or whether they show odd banding, strange clumping, or alignment patterns that don't match simple physics. If you spot internal layers that repeat in a weird way, or clusters that look like colonies stuck in mineral, your brain immediately jumps to terrestrial analogues where microbes either built or modified similar textures. It's not proof. It's not even close to proof. But it changes how seriously you look at the sample and how carefully you cross-check other data. Even if the shapes look interesting, you still need to ask, is there any trace of actual carbon-based chemistry stuck in or around this thing? That's where SAM, the sample analysis at Mars Suite, becomes critical. If the team decides to drill near or into the crystal-bearing rock and send powder into the rover's internal labs, SAM can heat the sample in steps and sniff the gases that come off. It can look for simple and complex organic molecules, carbon-bearing compounds that, on Earth, are often linked to life, but can also form without it. The key is context and co-location. If you see organics in random dust, that's interesting but vague. If you see even small spikes in organics in the same drilled sample that Chamin flags as containing this exotic yellow extreme brine mineral, the story changes. Now you're looking at a specific environment that had strong chemical gradients, strange water chemistry, and trapped carbon compounds. That combination moves you up a level, from odd geology to this is a preserved chemical environment where life, if it ever appeared on Mars, would have at least had a chance to survive or leave traces. But let's say the chemistry is extreme, the textures look suspicious, and Sam sees organics. Why can't you just say we've found life and be done? Because Mars is not Earth, and abiotic processes can trick you. You can grow complex, layered minerals in the lab with no microbes at all, just by cycling temperature, pH, and concentration. You can generate organics from non-biological reactions, especially when you have volcanic gases, UV radiation, and mineral surfaces helping. Redox gradients can appear purely from water reacting with rock under changing conditions. When you step into a completely different planetary environment, where pressure, temperature, and atmospheric composition are not like home, the number of false positive pathways goes up. That's why the burden of proof is brutal. To claim life, you would need multiple independent lines of evidence, all pointing to biology, and all ruling out known abiotic routes. Curiosity was not built with that full toolkit. It can hint, it can flag places where the chemistry is strongly suggestive, but it cannot close the case. So what can you say, if you're being honest and still taking the data seriously? You can say that this object, this strange yellow crystal crushed under one wheel, marks one of the most promising chemical environments for life that Curiosity has ever seen. You can say that the water that formed it was not mild and boring, but full of energy gradients that life could have used. You can say that its preservation inside the rock gave you a protected record of that environment, a snapshot of a niche that might have been habitable in a very specific, extreme way. And you can say with no exaggeration that this is exactly the kind of sample future missions, built specifically to hunt biosignatures, should target for return to Earth. The line you cannot cross is the one where you turn "this could have supported life" into "this proves life was here." And once you accept that, you hit the next problem. If this rock really does record such a special environment, you have to know when exactly in Mars history it formed, because that timing decides whether you're looking at a planet still waking up or one already dying. How do you put a date stamp on a rock from another planet when you can't bring it home and slice it up in a lab? Curiosity actually has a way to do rough dating on Mars itself using potassium-argon Kr methods. The idea is simple, even if the details under the hood are messy. Some potassium in the rock is a radioactive type called potassium-40. Over time, it decays into argon-40, a noble gas. When the rock first forms and locks in its minerals, the argon counter is basically at zero. As time passes, more and more argon-40 builds up inside the crystal structures. If you know how much potassium-40 you started with, and you can measure how much argon-40 is in there now, you can estimate how long the clock has been running. Curiosity does this in situ by heating samples and measuring the gases that come off, while other instruments estimate how much potassium is in the rock. It's not as precise as a full Earth lab, but it can tell you whether a rock is on the order of billions of years old or just hundreds of millions. If the yellow crystal-rich rock gives you a KAR age that lines up with known phases in Gale's lake history, early deep lake versus late shallow brine, you start tying its extreme chemistry to specific chapters in Mars's story, not just a long time ago. But knowing when the rock formed is only half the time story, right? You also need to know how long its surface has actually been sitting out there getting hammered. Cosmic rays don't just damage rocks, they also leave behind a measurable signature. When high-energy particles slam into atoms in the rock, they can create new isotopes, cosmogenic isotopes that only appear when you've been exposed at or near the surface. On Earth, people use these to figure out how long rocks have been sitting on mountaintops or at the surface of glaciers. In principle, you can do the same thing on Mars. You look at certain isotopes and their abundances, and from that you estimate how long that piece of rock has been naked to space. Here's the key idea. If you could compare the outer rind of the rock to the interior that holds the yellow crystals, and you saw that the outer part shows millions of years of cosmic ray exposure, while the interior effectively shows zero, that would be strong, independent evidence that Curiosity really did crack into a long-shielded core. Even when the rover can't do the full isotopic breakdown on Mars, the concept still guides the interpretation. You're always asking, does this rock look like something that has been out in the open for ages, or something that was buried and only recently pulled toward the surface? And you're not relying only on radioactivity and cosmic rays, you also have the basic old-school tool of geology. Where in the stack is this thing actually sitting? Even without exact radiometric ages, Gale gives you a relative timeline, a layer cake you can read. Curiosity knows its approximate elevation. It can see which units of rock it has already crossed, and it can map the relationships between layers. So you look at the context of this crystal-bearing rock. Is it part of a bedded, fine-grained lake sediment layer, deeply embedded in older deposits? Is it in a younger, overlying unit that represents a later period of sedimentation? Or does it cut across layers as a vein or fracture fill, meaning fluids move through cracks long after the original sediments were laid down? That geometry matters. If the crystals sit in a layer clearly tied to the main lake deposits, they probably formed while Gale still held standing water. If they are in a higher, more erosional unit, they might be tied to a drying period or post-lake groundwater. If they fill fractures, they might mark late-stage fluids squeezing through already hardened rock. The relative position helps you decide whether you're seeing main-phase lake chemistry, late-stage evaporation, or some post-lake alteration event. So why are we pushing so hard on dates and positions? Isn't weird and chemical enough to make this interesting? Because time is a constraint on habitability. If these crystals formed early, they may record a period when Mars' climate was still relatively mild, when the atmosphere was thicker, and liquid water was more stable on the surface. In that case, you're looking at an environment where life, if it ever appeared, might have had longer, more continuous windows to adapt, spread, and change the local chemistry. If the crystals formed late, they might belong to a dying world where water only appeared as short-lived brines, triggered by brief warming events or impacts before freezing or evaporating away again. That kind of environment is still chemically rich, but it's harsher and more episodic, giving potential life less time to operate and fewer chances to leave behind clear traces. The same mineral could mean a long, stable, habitable phase or short, extreme last gasp, depending on when it crystallized. So time isn't just a number you write in a paper, it tells you how big the window was for biology to do anything at all. And here's the part that really puts pressure on old models. What happens if the different clocks don't agree with the story you've been telling about Mars for decades? If the chemistry, the KR dating, the exposure age, and the stratigraphic position all point to concentrated brines existing at a time when your climate models say Mars should already have been locked in deep freeze, you have a problem. Maybe the crater floor stayed warm longer than average because of local heat flow. Maybe groundwater systems stored and released liquid water much later than expected. Maybe the atmosphere went through short, intense warm spikes triggered by volcanism or changes in tilt. Whatever the mechanism, it means your simple, smooth timeline of early wet Mars, then steady dry Mars doesn't hold. The crystal becomes a time-stamped message from a climate regime you didn't know existed, a mode where extreme water chemistry was still running, even as the planet as a whole was supposed to be dead and frozen. That forces you to rebuild your story of how fast Mars changed, how often it flickered back into marginal habitability, and how many hidden episodes of strange chemistry might still be waiting in other craters and valleys. And once you start rewriting the planet's timeline based on a rock this strange, the next brutal question naturally follows. Before you trust what it's saying about Mars, are you absolutely sure this thing isn't actually ours? A piece of Earth hardware or contamination pretending to be Martian? How do you know you're staring at a Martian mystery, and not just a piece of your own hardware pretending to be science? Before Curiosity ever left Earth, it went through harsh cleaning and baking to meet planetary protection rules. Critical surfaces were scrubbed and heat-treated to drive down the number of viable microbes and organic residues by orders of magnitude, far below what you'd find on a normal kitchen counter, or even in a hospital room. That does not make the rover perfectly sterile. There are still some spores, some organics, especially deep inside or in protected gaps, but it means that any Earth biology or contamination on the outside is extremely sparse and mostly shielded. The point of that effort is simple, so that when you see something strange on Mars, your first answer is not automatically "we brought that." Even so, for a find this weird, you have to seriously test the possibility that the rover itself is the source. So you start with the most basic suspicion. Could these bright yellow fragments just be pieces of Curiosity's own body scraped off by a bad wheel hit? The rover is not just metal and rock dust, it has paints, coatings, thermal blankets, adhesives and insulation, some of which can be off-white, tan or yellowish. In principle, a hard enough impact could chip something off a wheel or nearby structure, throw it onto the ground and make it look like a foreign object. But this is where the engineering work on Earth pays off. The team knows exactly what materials went into every external component, what polymers, what pigments, what metal alloys and in what proportions. Those materials have distinct elemental signatures. ChemCam and APXS can analyze the yellow crystals and compare their element mix to that database. If the crystals do not show the elements you'd expect from a coating, no titanium dioxide from white paint, no weird alloying elements from a specific bracket, no carbon-hydrogen patterns that scream polymer, then the idea that this is just a chip from the rover starts to fall apart. If instead the crystal composition lines up with typical Martian rock elements but in strange ratios, with no trace of human-made mixtures, you can confidently say this is not a piece of insulation that flaked off. Even if the chemistry doesn't look like any rover material, you still have to ask, did the wheel impact itself, do something unusual that could have caused hidden damage? Here, you lean on the rover's telemetry. During that crunch, Curiosity recorded wheel torque, slip, and vibration. Engineers can run that data through mechanical models to estimate the forces involved. If those forces are within the normal driving envelope, similar to what the rover has handled hundreds of times, then it is unlikely that this one event suddenly scraped off some deeply buried, never-before-seen piece of hardware. You can also look at the mission history. Have previous drives with similar or higher loads ever produced strange fragments in the images, or weird chemical signatures that turned out to be rover bits? If the answer is no, and if this drive looks normal on the engineering side, then the idea that the yellow material is rover debris gets weaker. The wheel broke a rock, that much is clear, but nothing in the contact dynamics suggests it also shaved off something exotic from Curiosity itself. Let's say at this point you accept the mineral is Martian. You still have one more contamination path to worry about. What about Earth organics or rover chemicals stuck on or around the crystal? Even if the rock is native, there can still be hitchhikers. Cleaning agents, plasticizers from cables, tiny amounts of lubricant, or surviving Earth organics might have transferred from the rover to dust, then from dust to the fractured surface. That matters, because when you heat the sample in SAM and sniff the gases, you might see organic molecules that have nothing to do with Mars. SAM can specifically look for signature compounds, things like certain chlorinated solvents, known plasticizers, or decomposition products from spacecraft materials. If those show up in recognizable patterns, you can flag them as rover-derived. On the other hand, if the organics detected, if any, do not match the rover's known chemical fingerprints, and if their isotopic ratios, for example the balance between light and heavy carbon, look more consistent with Martian processes than with Earth contamination, you tighten the case that what you're seeing is genuinely Martian. You strip away Earth's chemical fingerprints layer by layer until what's left is native. Once you've beaten on the contamination hypothesis from every angle, you reach a critical threshold. What happens when there's nothing left to blame but Mars itself? The moment you can say it with high confidence, this mineral phase and its chemistry do not match any rover material, and any organics associated with it are not from our cleaning agents or hardware. The whole narrative flips. The question stops being, what did we drop on Mars? And becomes, what did Mars grow that we've never seen before? That is a much bigger, much more uncomfortable question, because now every strange peak in the spectrum, every odd ratio, every unusual diffraction line is not a quality control issue. It is the planet talking directly. The yellow crystal is no longer debris, it is a signature of Martian geochemistry operating in a mode that Earth almost never uses. And once you accept that, you have to turn outward and ask, does this object look anything like the Martian rocks we've already caught as meteorites, or the weirdest minerals we've catalogued on Earth, or are we genuinely off the map? How do you tell if Mars has just shown you something that doesn't exist in any collection on Earth? You actually start with Mars samples that are already here. We have a small library of Martian meteorites, the SNC group, shergottites, naclites and chassinites. They are mostly igneous rocks, basalts and related types, forged in magma, not in lakes. Their mineral compositions tell you what normal Martian crust looks like, what typical basalts, typical pyroxenes, typical feldspars and olivines look like in terms of element ratios. When you put the yellow crystal's composition on the same plots as those meteorites, you're asking one blunt question: does this fit anywhere in the spread, or is it off on its own? If the sulfur, chlorine, sodium, magnesium and other elements sit way outside the ranges you see in SNC meteorites, then you're not just seeing an odd variant of known crust. You're staring at a part of Martian geochemistry that the meteorite record hardly samples at all. A part that didn't make it into the rocks that got blasted off Mars and landed here. But what if Mars isn't doing something totally unique? What if it's just doing, in a crater, what Earth already does in its harshest corners? On Earth, you know where to look for bright yellow minerals, acid mine drainage zones, where oxygen-rich water flows through sulfide-rich rocks, making highly acidic metal-loaded streams, volcanic fumaroles, where hot gases rich in sulfur and chlorine escape from vents and condense minerals as they mix with air, evaporating salt flats, where closed basin lakes dry down and drop out layers of sulfates, chlorides and mixed salts. These places produce vivid colours and extreme chemistries, not because of life, but because of tough interactions between water, rock and gas. So you take the Martian crystal's elemental composition, the sulfur to calcium, sulfur to iron, chlorine levels, trace metals, and compare it to datasets from those Earth sites. If it lines up with something like jarosite from an acid mine, that pushes you toward an acidic oxidizing brine story. If it looks more like deposits from volcanic gas vents, rich in certain halogens and metals, that points to a fumarole type environment. If it resembles layered evaporites from salt flats, it pushes you more firmly into the drying lake camp. Each Earth analogue is like a template. The closer the match, the easier it is to reverse engineer what Mars was doing. But you don't stop at passive comparison, right? You also try to actually rebuild this thing under controlled conditions. Back on Earth, scientists have Mars chambers, vacuum systems where they can set the pressure to a few hundred pascals, the temperature to about 210 to 240 Kelvin, that's around minus 63 to minus 33 degrees Celsius, or -81 to -27 Fahrenheit, and the atmosphere to mostly carbon dioxide. They can mix brines with ion ratios similar to what Curiosity infers from its measurements: calcium, magnesium, sodium sulfate, chloride may be perchlorate. Then they let those brines evaporate, freeze, thaw, and cycle under Mars-like conditions. The goal is straightforward. Can you make a mineral that has the same elemental mix and crystal structure as the Martian yellow material? If you can reproduce the diffraction pattern that Chemin sees, plus the same general element ratios that ChemCam and APXS report, you're closing in on a plausible formation pathway. Maybe it takes a certain cooling rate or a specific sequence of evaporation and freezing. Each successful lab simulation tightens the story, turning weird rock into product of this exact kind of brine under this exact kind of climate. Even if you can match it in the lab at small scale, you still have to ask, how widespread is this stuff on Mars itself? That's where orbital and surface spectral libraries come in. Orbiters like CRISM and Omega have scanned large portions of Mars, building catalogues of spectral signatures for minerals at resolutions of tens to hundreds of meters per pixel. Curiosity and other rovers add high-resolution surface spectra, zooming in on specific rocks at centimeters to millimeters scale. You can take the mystery mineral's spectral fingerprint, however approximate, and search for that shape in orbital data. If it shows up nowhere, or only in a few tiny patches at the edge of detection, that means it's either very localized or too subtle for orbiters to see against the mixed background. That is exactly the kind of material a rover is built to catch, something that occupies only a small outcrop or even a single boulder. A rock so rare that the planet's big picture instruments barely register it, while a rover happens to roll right over it, is the definition of a unique find. It means this is not part of a global layer of bright sulfate. It's a local, concentrated special case. But what happens if you've gone through all of that? Earth rocks, meteorites, lab simulations, orbital comparisons, and nothing really fits. That's when things get uncomfortable in a good way. If the yellow Martian crystals do not match known phases in SNC meteorites, if they don't line up cleanly with any standard sulfate, chloride, or mixed salt from Earth's acid mines, fumaroles, or salt flats, and if even your best lab attempts under Mars-like conditions only get close but not quite right, then you are looking at a mineral that may form under conditions we simply don't have on modern Earth, or that we don't preserve well here. Maybe it needs a combination of ultra-cold, low-pressure, high-radiation, long-duration brine cycling that Earth's climate doesn't offer, or that erases itself quickly. Maybe it depends on a slow trickle of volcanic gases into a deep, freezing basin over millions of years. Whatever the exact answer, you've left the comfort zone where Earth experience gives you a direct one-to-one match. At that point, the rock stops being just another sample with weird numbers. It becomes a window into alien geochemical logic, a way of using water, rock, and atmosphere that a planet like Mars can pull off, but a planet like Earth almost never does. And once you admit that Mars can run chemical experiments that don't have clean analogues here, you have to rethink how simple you thought its climate and geology were. So if a single crushed rock can already force you to throw out the old simple Mars picture, what happens when you plug that rock back into the bigger story of the planet, its climate, its lakes, and its chances of ever hosting life, and realize the shockwave doesn't stop at Mars at all? How much of Mars science breaks when one rock refuses to behave like the rest? For decades, a lot of models treated Mars as fairly simple. You had a volcanic crust, some water early on, maybe lakes and rivers for a while, and then a slow, one-way freeze-out into the cold, dry world we see today. That picture is clean, it's easiest to simulate, and it fits a lot of broad data. But a bizarre, highly concentrated mineral phase locked into bright yellow crystals in Gale Crater pushes back hard on that story. To get chemistry this extreme, you're not just talking about there was water, you're talking about water that was driven to the edge, pushed into intense separation of ions, possibly fed by hydrothermal pulses from below, and evaporated into extreme brines at the surface. That means Mars wasn't just running one simple script. It was running a more complex playbook, with episodes where chemistry went off the charts, where lakes didn't just quietly dry up, they turned into reactors. So what does that do to our climate models, the ones that said Mars should be too cold and too thin air to do this kind of thing at that point in time? If the crystals really demand high evaporation rates, or narrow windows of temperature and pressure, then the climate models have to move, not the rock. Maybe there were short, warm spikes, driven by bursts of volcanism that pumped greenhouse gases into the atmosphere. Maybe changes in Mars's tilt, its obliquity, periodically cranked up the sunlight at certain latitudes, thickened the atmosphere a bit, and allowed liquid brines to persist longer. Maybe groundwater kept feeding the basin far later than surface conditions alone would allow. The rock becomes an anchor point, a fixed "this happened here" marker that any serious Mars climate model has to hit. You can't just say the planet was frozen solid by then, if a real mineral in a real crater says, no, conditions were wild enough at this place and time to grow me. If one rock can push models around like that, where does it sit among everything else Curiosity has already found? Curiosity has a long list of headline results: ancient lakebed mudstones that prove standing water, clay minerals that track neutral to mildly alkaline conditions, detections of organics that show carbon chemistry was active, radiation measurements that define how harsh the surface is for potential life and for future astronauts. All of that is huge, but this yellow crystal changes the ranking. It may not be screaming life the loudest, but it is screaming, you underestimated how extreme this environment could get. That matters, because habitability isn't just about having water, it's about having a range of chemical niches from mild to extreme where complex chemistry can run. This rock redraws the internal map of Gale. It shifts the where would you most want to look again zones toward places where the chemistry went to the edge, where lakes became chemical soup instead of simple puddles. So once this shows up, do you only stare at the new data, or do you have to go back and reread a decade of old measurements with fresh eyes? You absolutely go back. Suddenly, old must come images that showed slightly unusual tones, but not as dramatic as this, look more interesting. Old ChemCam spectra that were pushed aside as noisy or odd but not important get pulled back up. A PXS measurements that were slightly sulfur-rich or chlorine-rich, but not extreme enough to cause a fuss at the time, now get replotted with this new point in mind. You start asking questions like, were there almost versions of this mineral earlier in the mission, partly weathered, more mixed with other phases, so they didn't stand out? Did we already drive past weaker cousins of this stuff years ago and just label them as minor oddities? The discovery forces a retroactive rewire of the entire dataset. You're no longer just cataloguing rocks, you're scanning for a pattern of rare, chemically extreme patches that together could outline a whole hidden phase in Gale's history. And what does that do to the big picture story you tell the public? The one where Mars is a long-dead desert that briefly flirted with water. That story stops working. After this, you can't honestly describe Mars as a simple cold desert with a short, boring, wet phase bolted on in the beginning. You have to treat it as a planet that ran a complicated sequence of chemical evolutions in its lakes and crust. There were early, more benign waters that laid down clays, later more concentrated brines that grew extreme minerals, and probably multiple cycles in between. The crust didn't just sit there. Fluids moved through it, veins formed, fractures filled, and then later events overprinted earlier ones. The most mysterious object, this single crushed rock with yellow crystals, becomes a physical argument against that old, tidy, low-complexity Mars. It says, you missed chapters. It says the planet's chemistry did not shut down when the climate cooled. It changed mode and kept going in ways your earlier models did not bother to include. And once Mars stops being a simple, one-track story, you have to face a bigger question. If a nearby world you thought you understood can hide this much complexity in one crater, what does that say about all the other planets, moons, and exoplanets you're trying to judge from a distance based on far less data than a single rover wheel crunch? How much does one strange rock on Mars change the way you think about planets you will never visit? Mars is not some exotic giant, it is a small rocky world, about half Earth's diameter and only around 11% of Earth's mass. A lot of the exoplanets we've found so far fall into that same size range, smaller than Earth, bigger than the Moon, sitting in or near their stars may be habitable zones. If a world like Mars with basic ingredients, basaltic crust, some water, and a thin atmosphere can still generate extreme mineral phases like these yellow crystals, just from ordinary water-rock reactions and climate cycles, then high chemical complexity is probably not rare. It suggests that on many small rocky planets, even ones that never had forests or oceans, you can expect weird brines, unusual minerals, and layered chemical histories. The default might not be simple dry rock. The default might be hidden chemical diversity, waiting in basins, fractures, and buried layers. That leads straight into a harder point. Do you really need biology to make complicated chemistry at planetary scale? If these crystals are purely abiotic, formed with no help from microbes, then they prove something uncomfortable but important. You do not need life to make intricate mineral structures in extreme niches. Geophysics and climate are enough. Gravity shapes the basin, volcanism builds the crust and releases gases, orbital cycles modulate temperature and pressure, and water does the rest through freezing, melting, and evaporating. Together, those processes run what is basically a natural chemical lab across millions or billions of years. So when you look at exoplanet atmospheres with telescopes trying to spot gases that might be linked to life, you have to be ready for confusion. After a few tens of millions of years, purely geological and climatic processes can build up odd mixtures of gases and surface minerals. You will have to separate signals that really need biology from signals that can be produced by planets doing what Mars did in Gale Crater, pushing their chemistry to the edge without a single cell involved. So maybe the old way of drawing a habitable zone around stars is too simple, not just in distance, but in what it assumes water will actually do. The classical habitable zone is defined as the band where liquid water can exist on a planet's surface, usually described as not too hot, not too cold. But the crystals in Gale point to another level of detail. It's not just is there liquid water, it's how does that water behave over time? Does it form long-lived lakes? Does it sink underground into hydrothermal systems? Does it become dense brines that survive below freezing? Evaporating lakes, deep brine pockets, and hydrothermal fluids expand the useful habitable space in both time and chemistry. An exoplanet that looks marginal in simple models, maybe it spends only a short period in the classic habitable zone, might still host brief but intense episodes where water and rock interact hard enough to build extreme mineral archives like this. That doesn't guarantee life, but it means the range of planets that can host interesting prebiotic or energetically rich environments is wider than a simple distance-based habitable zone suggests. And there's another twist. The end of a planet's comfortable era might actually be when its chemistry gets most interesting. Mars shows you that even as a planet cools, loses atmosphere and dries out at the surface, it does not instantly shut off chemically. Late-stage brines, created as the last pockets of water get squeezed and concentrated, can drive some of the most intense reactions. Evaporation events at the tail end of a planet's wet period may be short-lived compared to the total age of the world, but during those windows, the chemistry can be far more extreme than in the earlier, milder phase. A dying planet might go through a final burst of complex chemical activity, with brines circulating, salts precipitating, and minerals forming that never appeared during the calm middle period. The mysterious yellow crystal, then, is not just a memory of a lake, it is a fossil of that late-stage behaviour, a record of what happens when a planet is transitioning from sometimes wet to almost completely dry, and squeezing the last chemical potential out of its remaining water. So what's the unsettling bottom line when you take all of this and apply it beyond Mars, out to the hundreds of billions of rocky worlds you will never see up close? If a half-frozen, thin-aired, radiation-blasted world like Mars can hide a mineral this bizarre for billions of years, in one crater under one rock and only reveal it when a single rover wheel hits the right spot at the right time, then your intuition about other planets is probably far too conservative. You really do not know what is sitting on the surfaces of other planets and moons, trapped in buried lakes on icy worlds, locked in high-pressure mantles of super-Earths, or stored in salt deposits on exoplanets that briefly had seas. You're not just underestimating Mars, you're underestimating the whole cosmos's ability to turn simple ingredients into unexpected materials and complex chemical environments. And you're doing it while working from data that, compared to what Curiosity has in Gale, is barely more than a few pixels and some average spectra. So if this is what you get from one slow rover crunch in one crater on one small planet, the pressure lands hard on the next step. What do you actually do with this knowledge when you plan the missions that come after Curiosity? The ones that have to decide which 10 grams of Mars to bring back to Earth and which billions of rocks to leave behind. What do you do as a species when a single crushed rock makes you realize you've been asking Mars the wrong level of questions? Start with the obvious move, you change what you decide to bring home. If this yellow crystal-rich rock had been drilled by a rover designed for sample return, and the powdered core had been sealed in a tube, it would instantly jump to the top of the Bring This Back to Earth list. 10 grams of that material less than a tablespoon could be worth more scientifically than kilograms of more ordinary basalt or mudstone. That's not exaggeration, that's just information density. In that tiny mass, you would have a record of extreme brine chemistry, climate timing, and maybe even trapped organics, all in one place. So future missions get planned with that scenario in mind. You don't just say, let's sample representative rocks. You say, if you see anything this extreme, you stop, you drill, you cache. Landing sites, traverse plans, and sample priorities will all shift a little towards, what if we hit the jackpot by accident again and this time we're ready to pick it up? But to avoid relying on pure luck, you also have to upgrade the tools you send, right? Because Curiosity just showed you where its own limits are. Curiosity's payload was cutting edge when it launched, but this rock exposes the gaps. You know now that you want higher resolution imaging on the surface, cameras that can push well below tens of micrometers, so you can read textures almost at the scale of individual grains and microlayers. You want in situ Raman spectroscopy, a laser technique that can identify specific molecular bonds and mineral phases directly, without needing to drill and process as much. You want better organic detection limits, instruments that can sniff out tiny amounts of complex carbon compounds without confusing them with rover-derived contamination or perchlorate breakdown. And you want microscale isotope measurements, the ability to measure ratios like light versus heavy sulfur, oxygen, or carbon on spots smaller than a grain of sand. The mysterious object becomes the poster child in every instrument design meeting. People can point to it and say, if we had this tool, on that day at that rock, we would already know whether this thing formed in one event or a many, at what temperature and in what kind of water. That argument is very hard to ignore when you're locking in the payload for a rover that might not launch for another decade. Then you have to tackle a harder problem. Where do you even land next if you're hunting for the kind of weirdness this crystal represents? In the past, landing sites were chosen by balancing engineering safety and broad science interest. You needed relatively flat terrain, fewer big boulders, not too much slope, and at the same time you wanted layered rocks, ancient deltas, or other signs of water. After this, the science side gets more aggressive. They are going to push for places where orbital data, those coarse maps at tens of meters per pixel, show small localized chemical anomalies. Maybe it's a single bright patch in a sulfate map. Maybe it's a strange pixel in a chloride deposit. Maybe it's a unit with very unusual spectral ratios that nobody quite understands yet. These areas might be rougher, a bit more dangerous to land in or drive across, but they're also the likely homes of similar, accidental discoveries. You don't want the safe average patch of Mars anymore. You want the messy intersection zones where water, rock, and climate did something unusual. Landing site criteria get stricter and weirder, and the risk tolerance for landing somewhere a little more challenging creeps upward because the payoff could be a rock like this, or something even stranger. Of course, to even find those weird little zones from orbit, You need the spacecraft above and the rovers on the ground to work as one system, not as separate missions. Orbiters like MRO, with instruments like CRI-SM, can map possible sulfate and chloride deposits at scales of meters to tens of meters. That's not enough to see single boulders, but it is enough to see tiny colour and spectral anomalies, 1 pixel here, 2 pixels there, that could mark highly concentrated mineral patches. Rovers like Curiosity and its successors can then do the microscopic follow-up, driving into those pixels, resolving them into individual rocks, and putting lasers and drills on them. The workflow changes. Instead of saying, let's just drive into this broad clay-bearing unit, you start saying, see that one bright odd pixel at the edge of the unit over by that subtle ridge? That's where we want to send the rover first. A single pixel from orbit, when turned into a crystal like this on the ground, can be the difference between a solid, respectable mission and a paradigm-shifting one. So mission planning starts to integrate orbital and surface data more tightly right from the beginning. All of this leads to a bigger strategic shift, because once you admit that tiny, rare minerals can carry this much information, you can't be satisfied with a handful of in-situ measurements forever. Ultimately, this discovery feeds straight into the argument for large-scale Mars sample return, and beyond that a dedicated Mars rock lab on Earth, not just one project but an enduring institute. Imagine a facility where hundreds of labs can share and cross-analyze these materials using instruments far beyond what any rover can carry, focused entirely on decoding Mars. The most mysterious object so far, this yellow crystal that Curiosity crushed but could not collect, becomes the pilot case you show to funding agencies and mission boards. You say, look at how much this one rock almost told us, and then think about what we could do if we had it on Earth, sliced thin, imaged at nanometer scales, analysed for isotopes at insane precision. You point at Gale Crater and say, if this was hiding under one wheel track, imagine what else we've been driving past, what's sitting unbroken in other craters, in old deltas, in buried ice. The pitch is simple. You either bring these rocks to Earth, or you accept that you're reading the universe's most interesting stories through a keyhole. And once you're thinking that way, once you're designing missions, instruments, and entire institutes around the idea that one accidental crunch can rewrite a planet, there's only one question left to close the loop. What does this rock actually do to your own story of Mars, of your place in the solar system, when you step back and see the whole chain of events that started with a wheel rolling slower than you walk? How much can the story of a whole planet really change because of one slow, boring move of a rover wheel? You started with exactly that. A slow aluminum wheel rolling over a rock at roughly walking speed, about 0.04 meters per second, around 0.09 miles per hour. Nothing special, no dramatic drill sequence, no high-value target call. This was supposed to be background driving, just getting from one planned outcrop to the next. But that everyday motion put a few hundred kilograms of force under Martian gravity through one small contact patch, and the rock failed in exactly the right way. It shattered and exposed a bright, chemically extreme, tightly structured mineral phase that had been locked inside for millions or billions of years. No one picked it out in advance from orbit, no one circled it on a map. Mars kept it quiet, buried and shielded, until the moment a nuclear-powered rover by chance crushed it open and dropped it into full view. That jump from routine wheel crunch to cosmic pivot is why this rock matters so much. So why call it mysterious when that word gets abused all the time? Here, mysterious is not marketing, it's a diagnosis. Current models of Martian geology, climate and water chemistry do not easily explain how this object formed, how it stayed preserved, and how it ended up at the exact place and depth where a rover wheel could reach it. To form it, you probably needed extreme brines, very specific temperature and pressure windows, maybe multiple cycles of evaporation and freezing. To preserve it, you needed burial deep enough to shield it from radiation, UV, and sandblasting, but shallow enough that erosion could eventually bring it near the surface. To deliver it under Curiosity's path, you needed just the right history of sedimentation uplift and erosion inside Gale Crater. The rock is basically a compact list of things your theories did not predict well, all stacked into one object that refuses to fit comfortably into the early wet then dry, nothing too crazy story. What does that do to the assumptions you were quietly relying on without realizing it? You thought Mars' chemistry was simpler than Earth's. Less water, less time, fewer moving parts. You thought the climate arc was roughly understood. Early on there was liquid water, later it froze and thinned out. End of story. You thought most surprises would be mild. A new clay here, a little more sulfate there, tweaks to a basic picture, not full rewrites. Instead, this mineral points straight at extreme brines, unusual thermal histories, and maybe pressure or burial conditions you did not fully account for. Suggest that lakes like Gale's did not just fill and drain, they went through wild chemical phases on the way down. That forces you to redraw the planet's entire evolutionary timeline, not just in broad strokes, but in the details of when and where certain kinds of water and certain kinds of chemistry were actually possible. And once one rock shows you that, how do you ever look at the rest of the planet the same way again? After this, ordinary on Mars stops being a safe word. Every smooth outcrop might hide a strange interior under a homogeneous surface layer. Every dust-coated boulder could be a geochemical time bomb waiting for the right fracture. Every wheel track might be one unlucky rock away from another extreme phase. The standard for what counts as surprising just jumped. Before, a modestly sulfate-rich rock was enough to get attention. Now you've seen that a single bright, concentrated crystal can carry more information and cause more trouble for models than dozens of normal samples. Curiosity hasn't just found a weird rock, it's changed what field geologists, modelers, and mission planners expect from the red planet. From now on, there is an unspoken assumption in the room. If you aren't seeing anything shocking, maybe you just haven't cracked the right rock yet. So where do you fit in this, sitting on Earth while all of this plays out 225 million kilometers away, roughly 140 million miles, through a robot you'll never touch? You're living in the moment where a machine guided from Earth but acting on another world can, by sheer accident, reveal that a neighbouring planet's chemistry is stranger and richer than people thought for decades. You get to watch in real time as one crushed rock forces scientists to rerun models, re-rank discoveries, rethink landing sites, and push harder for sample return. This isn't just a curiosity or a neat image in a newsfeed. It's a warning shot from the universe, a very clear message that says, if this is what you find by accident on Mars, with one rover in one crater, you are nowhere near ready for what is waiting on the worlds you haven't even landed on yet. The real implication is simple and a little ominous. The cosmos is more complicated than your plans, and it only takes one unexpected crunch under one wheel to prove it. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.